Thanks a lot for having me. It's a real pleasure to speak at this conference. So today I'm going to talk about a categorification of a lot of the ideas that were presented by Clement. And in particular, this is work in collaboration with Clement plus some upcoming work. Okay, so in 2+1 dimensions, particularly in the non-chiral setting, we have a pretty well-established collection of ideas, which can be summarized by the following commutative diagram. The idea is, given the data of a unitary spherical fusion category, then we have an algebraic construction called the center, which associates to this algebraic data an anion theory, which can be collected in terms of a modular tensor category. Now, as well as this kind of algebraic setup, we also have the kind of more classical condensed matter theory perspective. By using string nets, we can define a topological lattice Hamiltonian model, which I'll define briefly, but it's along the lines of what Clement was discussing. And the topological excitations in this theory are exactly described by this anion theory constructed by the center. So that's what I mean by this diagram commutes. Now, whenever I think about an anion theory, in particular modular tensor category, the kind of ideas that I have in mind are, given some space-time evolution for some topological phase in the 2-disk across times, this is a space-time of the 3-disk, then really my modular tensor category is a collection of rules that allow me to decompose some arbitrarily complicated space-time evolution into simple building blocks that are nicer to evaluate. And then I can compose them vertically in order to calculate my space-time evolution. Now, from this perspective, what my modular tensor category does is it collects as objects configurations of anions in the 2-disk, and the 1 morphisms correspond to isotopy classes of space-time evolutions, i.e. their world lines. And in particular, modular tensor category is braided and monoidal, and the monoidal structure tells us how to horizontally compose these blocks, whereas the braiding allows us to discuss the braiding of anions in the space-time. Now, what I want to talk about today is a lot less understood, at least for me, and this is the topic of non-chiral 3+1D topological phases of matter. So in this setting, it's conjectured that, well, at least a large collection of these models have a nice algebraic framework given by unitary spherical fusion 2 categories, as defined by Douglas and Reuter quite recently. And to this kind of data, again, we have a notion of center, which should give us what I'm going to call an extended anion theory. And by extended, what I really mean is that the excitations in this theory are no longer going to be just point particles, but they're going to be extended excitations like strings or loops, like in Clement's talk. And what we want to do is we want to understand some categorical package, which I'm going to call a modular tensor 2 category, as some nice way of discussing and describing this kind of physics. Now, recently, with work of Kong and Untitled, I think we'll be talking about this later this week, they were able to compute the center for a given model, so-called Dijkgraaf-Witten theory, with a spherical fusion 2 category, and they gave a nice description of it. And in today's talk, I actually want to talk about the other side of this diagram. So given some notion of topological lattice model, how can I understand the topological excitations and their relationships to an extended anion theory? And the way that I propose to do this is through what I call a categorified tube algebra. So before I get into the details, I want to describe roughly what I think of when I think about a modular tensor 2 category. I've put this in brackets because it's not a definition that we understand well or we really have a firm understanding of, but roughly speaking, there should be some kind of braided monoidal 2 category equipped with some extra conditions. And the extra conditions should be things like duality and some notion of remote detectability, i.e. an ability to detect our anions using topological processes. Now, when I want to do this, when I thought about a modular tensor category, I thought about decomposing my space-time into local chunks. In this setting, what I want to do is define a collection of rules that allow me to decompose the Hilbert space that this 3+1D theory applies to a 3 manifold, possibly with topological excitations within. I want to be able to decompose this into tensor factors and then describe this in a categorical package talking about local moves on these tensor factors. Okay, so when I just start saying that I want to decompose this, if I start by thinking about the Hilbert space of this 3-disk with a topological open string, for instance, in it, then the way that I want to package together my modular tensor 2 category is that I want to say that the anion, or I want to say that the point particles correspond to not just anyons, but they're actually going to be anionic point-like states which exist in a gapped boundary condition for this three-dimensional Hilbert space. Now, rather than isotopy classes of world lines, the one morphisms, I think, should correspond to a Hilbert space of the three-disk with open string excitations within it, possibly terminating on these gap boundaries. And the isotopy nature, or the topological nature, comes in the two morphisms, where we think about the two morphisms of being the space-time evolution, and this should be some kind of isotopy classes of string world sheets. Now, I said that this was monoidal. Again, the monoidal is this horizontal composition, and the braiding is what allows me to talk about under and over crossings of these string excitations, as well as braidings of their world sheets. So the kind of things that we want to be able to describe in this framework, at least a simple question, would be if I had a configuration of two closed loops embedded in the three-disk, then I could consider a space-time evolution where I pass one loop through another. Think about blowing smoke rings through each other. And as I evolve this process, these world sheets define a knotted surface in the four-disk, and we expect the amplitude for this process to only care about the isotopy class of this world sheet in the four-disk. But another motivation for breaking our Hilbert space into these local tensor factors is that, unlike point particles, our loop-like excitations can also appear in links. So if we thought about closed loop excitations, we could think about a configuration where we had three loops all being threaded by another loop-like excitation. And again, we want to be able to describe the space-time dynamics of this process, such as braiding, as well as fusion while they're linked. And more generally, we could think about some arbitrary, horrible collection of links, but we'd still want to be able to describe their space-time evolution and their physics to describe the topological phase. Okay, so coming back to this idea, I want to begin by talking about Hamiltonian models for topological phases of matter, and in particular, what I'm going to call a topological lattice model. And this is going to be the building block for everything I say from now on. Okay, so this follows almost identically to what Clement was saying. And so what I'm going to say is that a topological lattice model is a collection of rules which for every oriented D manifold sigma equipped with some discretization, i.e. some triangulation with some extra structure. And what it does is it defines for me a finite dimensional Hilbert space, which is just the free vector space over some classical field configurations, as well as a local Hamiltonian. So this Hamiltonian is going to be a sum of local operators, all of which have support in a local ball surrounding, say, a vertex of my lattice. And in the following, I'm going to assume that the local Hamiltonian operators satisfy the following algebra, which is to say that they are commuting with respect to a given ball, and they mutually commute as we spatially vary the terms. Now, in order to make our theory topological, what I'm going to do is I'm going to equip my lattice model with some extra structure, which is a family of unitary isomorphisms. And so given this Hilbert space, my Hamiltonian, this is a gapped Hamiltonian, so I can define a ground state subspace for a given triangulation of a manifold. And I'm going to say that if I have two discretizations of the same manifold, which agree on the boundary, then I'm going to equip my model with some knowledge of a unitary isomorphism mapping the ground state of one discretization to the ground state of the other discretization. And I really want to think about this as some form of symmetry of the ground state subspace. So it's going to satisfy some commutativity property with respect to the Hamiltonian operators. One thing I will note is that if I introduce manifolds with boundary, a priori, I'll always consider open boundary conditions. So the Hamiltonian constraints never act on degrees of freedom on the boundary, only on the interior of the manifold. Okay, so I've defined very briefly what I mean by a topological lattice model. Now, at the beginning of my talk, I was promising to talk about the excitations. And how I want to talk about the excitations is through what I'm coining the categorified tube algebra. Okay, so an algebra can be defined quite generally. So given a monoidal category C, an algebra is a pair consisting of an object and a morphism from A tends to A into A itself. And this satisfies some condition, which you can roughly think of as associativity, what it means to be associative inside a monoidal category C. Now, in the following, I want to talk about two algebras, or categorified algebras. And in analogy with algebras, I want to say that given a monoidal 2 category B, a 2 algebra is going to be a triple of an object of one morphism, just like in the algebra setting. But now I want a 2 isomorphism, which weakens this associativity diagram. And these 2 isomorphisms are required to satisfy some coherence data, which you can think of as relating the different ways of composing 4 copies of the object. I think I will note here that I'm going to use 2 category, but sometimes it might be by category, but I'm just going to use 2 category generically.
Excuse me, I have a question here. So a different object, that corresponds to different algebra. So this category is a collection of algebra. So different object is different algebra. That's kind of this way.
Kind of like it's so rather than thinking about a collection, it's just it's something I can define within the context of the category. So it's just a monoidal 2 category, but within this I can define a notion of 2 algebra whenever I have a triple of this data. Is that okay?
But my question is that you have object, you have different object. Is that different object correspond to different algebra?
Yeah, a different object corresponds to a different algebra, completely.
Okay, yeah.
So each choice of these triple defines a different algebra. Okay, and so in particular, the categorified true algebra I'm going to define is going to be a 2 algebra in the symmetric monoidal 2 category of vector module categories. So this is just the higher, if you think about an ordinary vector space as being a module over, say, the complex field, then I'm going to say that a 2 vector space is going to be a module over the category of vector spaces.
Okay. Sorry, with respect to that definition, why are you calling it an algebra as opposed to like a semi-group or something, like a weak semi-group?
Yeah, so we could call this like some kind of pseudo-monoid in a 2 category, because in the rest of my talk, I want to use the term algebra rather than pseudo-monoid. And so you could think about this as a pseudo-monoid, or everything I'm going to do is going to be linear, which is why I'm secretly calling it an algebra.
Okay, thank you.
Okay, now the underlying idea of the categorified tube algebra is very similar to what Clément was talking about with the tube algebra itself. And so what we're going to do here is, given a topological lattice model, we can define a Hilbert space to a 3 manifold, and using a technique very similar to the tube algebra, what we're actually going to do is we're going to, using the data of my topological lattice model, I want to define a 2 vector space to a 2-dimensional manifold with boundary. And the idea here is that a 2 vector space in the rest of this talk is a semi-simple abelian category, or equivalent, you can think about it as the category of modules for a semi-simple algebra. And so using this notion, I'm going to define a 2 vector space. And then given this 2 vector space, I'm going to form a product and a 2 algebra internal to the category of 2 vector spaces. And similarly to what Clément was saying, the reason I call it a tube algebra is that it's based on this product will be based on the idea that given a pair of cylinders, I can glue them along a common boundary, and then I can use some orientation and boundary preserving diffeomorphism to shrink this union back to a single cylinder. And then what I'm going to do in the last part of this talk is explain that or motivate why I think that this extended anion theory is nicely captured by the representation theory of this 2 algebra. Okay, so let's begin with this idea of a 2 vector space for the cylinder. So given a 3+1D topological lattice model, I can define a Hilbert space, and in particular, a ground state subspace to any given 3 manifold. And so what I'm going to do is, given this 3 manifold equipped with a triangulation, and I'm going to not draw triangulations because otherwise it gets complicated, but let's assume that everything is equipped with the choice of triangulation. And this 3 manifold, I can really think of as being S1 cross the bigon. So bigon is kind of a 2 disk, and going back crossing S1 into the plane. So using this ground state subspace, what I can do is exactly like in Clément's talk, I can define a finite dimensional associative star algebra inside the category of finite dimensional vector spaces. And in particular, these 3 conditions guarantee that this algebra will be semi-simple. And the way that I do this is given the tensor product of these ground states, I pick some product state, and I can think about gluing this cylinder in, well, this manifold here inside this other one. And in order to do this, in order to glue the states, what I do is I have to say that the boundary condition on the exterior of here is the same as the boundary condition on the interior. And so I can match these two manifolds. And so if these field configurations align, then what I can do is I can compose these, and in some sense I'm defining a state on the Hilbert space defined by gluing this manifold inside another one. So I'm defining a state on these glued manifolds. And the reason that I've colored the gluing seam in yellow in this picture is that a priori, if I start off with some state in the ground state here and the state in the ground state here, there's no reason when I glue them that the Hamiltonian constraints, or these Hamiltonian operators, will be satisfied in a local neighborhood of the gluing seam. I've just not added this data in. And what I want to talk about is ground states, because this is where these topological lattice models are particularly prominent. And so what I can do is, using the fact that my Hamiltonian is formed out of projectors, I can project any given state which is excited into a ground state. And so what I do is I project this state on the glued manifolds into the ground state subspace. And then, using the fact that my theory is equipped with this family of unitary isomorphisms, I can again map some state on this triangulation, which shares the same boundary as this one, and they're both the same manifold. I can define an isomorphism which maps me back into a state of this Hilbert space. And I'm going to say that the algebra product is given by making sure that this diagram commutes. So it's just given by the composition of these maps. Okay. Now, using the fact that this algebra is finite dimensional and semi-simple, what I can do is I can define a two-vector space, i.e. a semi-simple abelian category of the cylinder, which, if I think about the boundary of this manifold, it's two copies of the cylinder, its outer boundary and the inner one. Then if I take the category of, say, right modules for this algebra, then I can define a category, and this category in particular is an example of a two-vector space. Okay, so now I've explained how to define a two-vector space to a cylinder. How do we define a categorified product? And in the following slides is kind of the manifold I was drawing was S1 cross the bygone, but I think that the diagrams get far too hard for me to draw if I keep keeping this S1 in. So I'm going to remove a copy of S1 in the following to make the diagrams easier, but it doesn't change the ideas. Okay, so if I thought about the tube algebra, if I thought about this process considering a bygone, not this kind of, I call it the double skin barrel, then what we do here is, if I calculate the category of right modules for the algebra, then this defines a two-vector space to the line, to the interval. Now, given any module for some semi-simple algebra, we can always think about this as a subspace of the regular representation. So we can use this ground state subspace of the bygone in order to define our right modules, and up to isomorphism, every right module will be some sub-Hilbert space of the ground state Hilbert space of the bygone. So this is what motivates this diagrammatics. And what I can do is, given two modules, so these are both vector spaces, I can identify field configurations on these boundary points in order to kind of glue them together in some sense. If these field configurations don't match, then I map this to the zero module, the module defined by the zero vector space. Now, when I glue these together, this isn't canonically a right module for the bygone. If anything, it's not even a manifold in the classical sense, because we have this pinching at the point. And so in order to define a right module out of this data, what we do is we make the following observation. If I'm given the ground state subspace of the bygone, but here the left edge is created out of two line elements, then this right edge is a single line element, so it has a natural action of the bygone algebra on it. So this is a right algebra for this bygone Hilbert space. But on the left-hand side, I can glue along this seam, so I can identify this edge and this. And so what I do is I take these Hilbert spaces and this one, and I glue them together. So I identify their field configurations and apply the Hamiltonian constraints along the seam. And now because this is a right module, I, in the category of modules, can just define some isomorphism of right modules to go back to one of the modules, which is a subspace of the regular representation. And when I'm defining a 2 algebra, it's not just enough to define a product, but I also need some notion of associative up to isomorphism. Now, using this lattice interpretation, or this kind of topological lattice model interpretation, we actually have a really nice option for the associator that pops up naturally. And so if I think about this manifold here, I could think about this as one form of the associate, like one choice of bracketing for the product on 3 objects. And so I compose 1 and 2 by gluing this chunk of space here, and I compose 1, 2 with 3 by gluing a chunk here. And the other associativity brackets is given on the right-hand side. Now, because these are interpreted as ground states of the 2 disk, then I naturally, these 2 discretizations are just changed by a boundary, a triangulation change in the bulk, right? There's nothing happening on the boundary. And so I can use this family of these unitary isomorphisms to relate the field theory here to the field theory here, the Hilbert spaces. And in particular, the composition rules, which come from some underlying TQFT description for these triangulation changes, guarantee that this rule is satisfied for higher order coherence relations. So this higher order coherence that I didn't define is automatically satisfied when we define this 2 isomorphism like this. Okay, so in Clement's talk, he was talking about topological gauge theory with a higher group, but also he mentioned the finite group case, and we can apply this construction quite nicely in this setting. And in particular, what we find is that if we calculate the 2 vector space of the cylinder in this topological gauge theory of finite group, and then what we find is the following multi-fusion category is our 2 algebra. And in particular, the objects of this category are given by finite dimensional vector spaces graded by a set of elements that look like this, which are actually the morphisms in the conjugation groupoid. And so we think about it as a vector space with a subscript. The morphisms in this category are grading preserving linear maps, and the 2 product is associative, and the product is given by basically if G prime is the conjugate of G by H, then we just take the tensor product of the underlying vector spaces and define the new grading like this. And if this condition isn't satisfied, then we define this to be the 0 vector space, which exists with no grading. It's like 0 in the group algebra. Okay, so in the previous slide, I said that associated to the cylinder in finite gauge theory, I said that the category was multi-fusion. So I'll be honest, I haven't quite proved yet that this construction canonically always gives you a multi-fusion category. I know for gauge theory and higher gauge theory it does, but I'm still ironing out the proof. But roughly speaking, I conjecture that this 2 algebra is always actually a multi-fusion category for any choice of 3+1D topological lattice models, as I defined previously. And the idea here is that this should really follow from some categorification of an inner product structure. And this is because we should really be talking about 2 Hilbert spaces, not just 2 vector spaces. And we can discuss this in the questions if people are interested in this. And for the rest of the talk, I'm now going to assume that this is true. So in the final part of my talk, what I want to do is I've defined this categorified tube algebra for the cylinder. And what I want to do is I want to look at the representation theory of this and try and relate this to things that I understand in lattice models, and in particular, trying to understand extended anion theories. So what I can do is whenever I have an algebra, it's quite well known that if you have an algebra, you want to study its category of modules. And so a module is just some vector space which emits an action from an algebra. In a similar vein, we can define module categories for a 2 algebra. And we can think about this as you have a category, and this is equipped with a, if we're doing this in 2 vectors, it's going to be a linear functor plus some additional coherence data. And we think about this bifunctor as being a map from our algebra tensor over this category into itself. So we have an action functor. And we can collect this category, these module categories into a 2 category whose objects are modular categories, the morphisms are modular functors, which are just functors between these categories, satisfying some relationships, ensuring like consistency with respect to this action, and two morphisms are natural transformations, again compatible with this action and some other data. Okay, but what we want to do is, if I want to relate this to physics, I want to give a more concrete representation or concrete description of this. And so two works that I particularly recommend if you're trying to think about these things is the work of Douglas and Reuter, and the work of Goethe and Johnson-Fried were both really nice areas for me to get into these things, as well as like the reference inside. So like if you want a more established references, I'd go with those. Okay. So yeah, okay. So roughly speaking, we defined what an algebra is inside a monoidal category. And so if we're assuming that this category is multifusion, it's monoidal. And so it turns out that modular categories for this multifusion category up to equivalence are described by a category of modules for a separable algebra in this category. And you can think about this as a generalization of semi-simple algebras, where you can define all of the modules in terms of idempotence within the algebra. Okay, now given a pair of modular categories defined like this, in a two category, we don't just have a collection or a set of morphisms between two objects, but instead we have a category of morphisms. And so in the setting, we call this the Hom category. And what's also nice to show is that the category of the Hom category for mod A and mod B, where these are separable algebras in here, is given by the category of AB bimodules in this multifusion category. So looking at these references, you can make these ideas precise. And before I give like a nice description of how these ideas relate to the physics, I just want to make an observation. So going back to my two vector space, I want to describe two nice ways in which you can define the morphisms in this category or two vector space. Now, one is that if we have some Hilbert space of the bigone as like some kind of regular representation, then if we change the triangulation in the bulk, you can easily show that this is an intertwiner for the right action of the algebra. And so this defines a morphism in this category. So internal triangulation changes is a morphism here. But the one that we'll use a lot next is that if I'm given some module and I'm given the ground state subspace of some manifold, which on the right-hand side, I can match with the left-hand side of my module, and on the left-hand side, it can be whatever you want, really, then actually I can define an intertwiner by gluing a state from this Hilbert space on the left-hand side of this module. And it's this idea that's going to allow us to relate this categorified tube algebra to ideas in the excitation spectrum. Okay, so whenever I have some AB bimodules, there's a nice way of defining this in terms of an algebra, and in particular modules for an algebra. And so I'm going to define an algebra whose module theory defines AB bimodules in our multifusion category. And so I'm going to call this A/B. So this is a morphism between mod A and mod B. And what I can do is I can say that this algebra as a vector space is the direct summand of the Hom spaces in my module category. So if this is a abelian category, then it's Hom spaces of vector spaces. And so I can form a vector space just by taking the direct summand over the collection of objects in this category of this vector space here. And so we just pick a representative set of objects and form this. Now, what I can do is, in this setting, is, so let's think of it. So if I take A tensor X tensor B, then I can define some right module as in the following. And if I want to define a Hom into some right module Y, well, what I can do is I can define some state which I can glue such that once I've glued it to the right, the corresponding right module is isomorphic to Y. And it's this idea of this state that we're going to use to talk about these bimodules. And so in particular, if I take a triangulation of the two disk and the Hilbert space on this, then what I can show is that this Hom space, so one of the factors of this direct summand, this Hom space is a subspace of this ground state. So we have a nice identification of this. And then this intertwiner or this morphism from here to here is nothing more than a state in this Hilbert space. Now I did this in the lower dimensional setting, but the same applies. In our 3+1D setting, where in this setting it's slightly harder to see, but in essence we find that the elements of this Hom space are just given by subspaces of the ground state of the annulus cross the interval. And I'm going to draw the states like this. So if I have an algebra, I need to define a product, and the product goes a little bit like this. So given a state here, so given one of the states in the cylinder and the annulus cross the interval, then what I can do is I can define the algebra product induced from the previous as an interpretation on the lattice, on our topological lattice model. And what we do is, I've chosen this, so this right state is glued inside this left one by identifying these cylindrical boundaries. This defines a state here. But the problem is that in my topological lattice model, all I told you how to do was change triangulations which preserve the triangulation of the boundary. Now this is where the notion of these kind of separable algebras comes in. So my separable algebra is a morphism from A tensor A to A, satisfying some additional constructions. And I can think about this again as a state. And it's a state of this funky looking manifold. Which I suppose, is it the suspension? Anyway, it's of this manifold here. And so if I have a notion of algebra, I've defined one of these states, which makes this product make sense. And so what I can do is using this idea, I can define the algebra product by gluing one inside the other one, and then gluing these states on the top and bottom. And so if I glue, so this edge is identified with this cylinder, and so it goes to the top. And then once I've glued it on, then I have my triangulation changes, which allow me to deform a state here into a state of the original form. And it turns out that you can argue very nicely that this is in one-to-one correspondence with the algebra required to define the bimodule objects. Now, what we want to do is we have this new algebra. It looks a lot like the tube algebra that Clement was discussing. And what we want to do now is relate this to the excitations in the theory, akin to what Clement was talking about. So what I could do is, if I'm given a copy of, so this is D2 cross the interval, I could think about having some open-ended string excitation in the theory. And so the idea is that in a local neighborhood of the string, we can tell its presence by a violation of the Hamiltonian constraints. And what we do is we say that if I have a gapped system, in particular these topological models are going to be the fixed points of my theory, then the correlations of the theory, the entanglement between some region A and region B, is in essence localized on the boundary. And so what I can do is if I take a local neighborhood of the string where the Hamiltonian constraints are violated, then what I can do is I can introduce a new boundary, and this boundary in some sense is defining the correlations between the interior of this excited region and the exterior. And so I can map problems about understanding these excitations into boundary theories. Okay, now, as in Clement's talk, just having a boundary theory is not enough, right? We need to decompose these boundary conditions with respect to some symmetry in the same way in gauge theory you look at the particles as being representations of the gauge group. It's about transformation properties. And so what we're going to do here is we can interpret, is we say that if we have these gluing rules, then what
Alex,
yeah.
Sorry. So, Xiaogang, you want to ask a question or you want to make an applause? I was just unsure because, did you want to ask a question? Okay, if not, sorry for interrupting. Yeah, Alex, please continue. Sorry.
Any questions? I don't know if people. Okay. And so what we can do is we can convert our statements about trying to understand these topological excitations into ideas about boundary conditions. But what we want to do is we want to find some symmetry in order to decompose these boundary conditions. And the natural symmetry we have in our topological models is length scale invariance. And so what we can do is, given this manifold here in classifying these boundary conditions, we can interpret this algebra product of stacking these cylinders inside and then deforming the triangulation. But we can think about this as a process of adding more space or performing a renormalization group action and then deforming it back to itself. So we're looking at an action of renormalization of this boundary by gluing these states. And in particular, this is exactly what we want when we want to talk about topological excitations, because these really should be excitations which are measurable at all length scales. Our topological theory exists in the low energy limit where our metric degrees of freedom vanish. And so this is a good principle for characterizing topological excitations. Now, using this idea, we say that we can associate a module for this algebra, and we can think about this as defining a length scale invariant Hilbert space for a string excitation. And what we're really doing here is we're saying that we're classifying topological strings, but because we're removing, in essence, all of the local data with this renormalization process, it's really an equivalence class of topological strings up to the introduction of a local excitation. In a similar way, this idea of we had some separable algebra, well, what this does is you can, by using some really nice arguments, you can show that the separable algebra corresponds to two things. First part of the algebra is the object, and that defines a way of defining gapped boundary conditions on the edge of this manifold. And the algebra property is telling us about the renormalization, or how to change the length scale of the theory stuck on the boundary. And so we can interpret the category of modules for this as describing anyons which are pinned to a possibly anomalous boundary condition of our spatial manifold. Now, using these ideas, if we have a two category, we can think about what the composition of one morphisms is. So if I think about a one morphism as being some Hilbert space with a string excitation in it, and I can think about the composition as stacking two chunks of 3D space together, and then the two morphisms actually give us a collection of rules to renormalize this. So here we've introduced a new boundary, which is kind of no longer the boundary as such, and the two morphisms in our category tell us how to get away this. So how to go from two strings with a kind of fictitious boundary, and then by renormalization style arguments, we can remove this boundary. Okay, so what I've done so far, or hopefully I've argued to some extent, is that if I have this category mod of the circle, then I've got some way of talking about Hilbert spaces of the 3-disk with possibly open strings inside. But at the beginning of this talk, I said that my 3+1D topological order should have some kind of monoidal structure, this horizontal composition I've not told you about, as well as some braiding structure, allowing us to define under and over crossings of these lines, and also their world lines. Well, in order for us to understand this, I'm just going to pose an observation and then some questions that I'm still trying to work out. So it's well known that if I have some category of modules and I want it to have fusion and braiding structures, then I define a Hopf algebra. Well, in our setting, if we have a topological gauge theory, I defined with this multi-fusion category associated with the cylinder in topological gauge theory, then what it turns out is that this category can be equipped with what's called a quasi-triangular Hopf category structure. And if you want to see more about this, I fully recommend the thesis of Neutral, which I think is called Representation Theory of Hopf Categories. And what this really does is this categorifies the usual ideas of Hopf algebras in a very nice way. And in particular, if I have some multi-fusion category in which I can equip it with a quasi-triangular Hopf category structure, then its category, well, its two category of modules actually becomes braided and monoidal. And additionally, the Hopf part means that it has jewels. Now, there's a very nice and easy way to map, to apply a quasi-triangular structure to this multi-fusion category. And if you do, if you calculate the representation theory as well as these braiding and monoidal structures, then what you find is we actually reproduce the result in Kong, Tian, and Zhao's work, which I think we'll be talking about on Friday, where they calculate the center of G-graded two vector spaces with cohomology, and you can show up to some equivalence of braided monoidal two categories that this is really the same thing. Now, an open question that I don't know how to answer quite yet, but I'm working on, is can we canonically put a quasi-triangular Hopf category structure, or in principle a weakened variant, on this multi-fusion category defined by a 3+1D topological phase? And if we can, there's a nice relationship between topological lattice models in 3+1D and spherical fusion 2 categories. Can we use this canonical assignment to verify completely that the center of this corresponding fusion 2 category is this braided monoidal representation category coming from the topological lattice model? And so this is what I'm working on at the moment. And before I end this talk, I'm just going to have one more slide. And this is a kind of dimensional reduction argument. And what it turns out is that given a two category, well, this kind of two category of module categories, I can define this notion called the dimension. And the dimension is a braided monoidal category consisting of pseudo-natural transformations of the identity two functor and modifications between them. And it turns out, in general sense, for any module category of a multi-fusion category, this is the same as computing the Drinfeld center of the multi-fusion category. So you can show this correspondence. And it turns out that if I think about what the center of this category is, using similar lattice model-induced ideas, then what I can show is that if I thought about the tube algebra for the torus across the interval, which is what was discussed in Clement's talk, then what I actually find is that the Drinfeld center of this has a very natural interpretation as corresponding to a category defining loop excitations in the theory, possibly with some threading between them. And by here, I've put this BR above to say braiding, where as it comes from a Drinfeld center construction, this additionally has the description of the fusion and the braiding of these loops while coupled to this background loop. And the motion group of this is often referred to as the linear necklace group. And I think that's everything that I want to talk about today. So thank you for